Alrighty, for the first part of today's lab, we're going to be looking at using MATLAB for model fitting. So the first thing that we want to do is import the data for the lab, which we actually, if you've been following along, I believe it was in the first lab, we actually would have imported this file modelfit.mat.mat from CUlearn. So this is actually the data that we'll be using for this problem. So to get that into our workspace, we just double click on it. Or alternatively, you could go to Home and then Import Data. So we now have the data there, and we want to take a look at this, see exactly what we're working with. Okay, so we have something that looks kind of roughly like like a parabola, like half of a parabola. So, for the purposes of this lab, one thing that we want to do now is we want to try a appropriate transformation from the ladder of powers to try to figure out which transformation will give the most linear looking plot. So in this case, like I said, to me at least, that looks to be roughly quadratic. I'll zoom in a little bit here, so hopefully it's a little bit easier to see on the video, especially if you're not watching in high resolution. Um, so since this looks roughly like a quadratic, I'm going to try creating a transformed y variable by doing a termwise exponentiation. In this case, going through and doing um, transforming each y value by putting it to the power of 1/2. So taking the square root of each thing. Theoretically, if this is a plot of y equals some function of x squared, then if we look at a plot of the square root of y, that should be dependent on x directly, giving a linear plot, or roughly at least. Um, and it's an important note here. If we do just the regular carré symbol for the exponent, then we'll get an error here because we have incorrect dimensions for raising matrix to a power. What we have to do, and this is something that we would have seen back in, I believe, Lab 1, but wasn't fully elaborated upon, for a lot of different operations like multiplication or exponentiation, you can make it termwise by putting a dot before the operator symbol. So in this case, we'd have y dot carré, then 1/2. So that goes through and takes the square root of each element in our y matrix. And now we can try plotting our transformed y against the x values. Did I call it y transformed? Yes. Okay, so there is a little bit of an anomaly at the first few points of data there. But after that initial dip, we can see that it looks pretty linear overall. So what we want to do now is we want to use um, MATLAB's linear model fitting function to try to get a model for the data. So to do that, I'll type in polyfit, and we have x as our independent variable and y transformed as our dependent variable. And since we're trying to get a linear model fit, we'll put 1 as the last element. The last, we have 3 different spaces, 3 arguments that we're filling, where we have independent variable first, dependent variable second, and then the order of the polynomial that we want for the model. So I will just execute that. So we get the coefficients on our polynomial that's fitting to the data in descending order. So we'd have 0.9591 x to the power of 1 minus 1.6698. But keep in mind, this is for the transformed data. So essentially we had y to the power of, I'm not doing this as a command, I'm just writing this down for illustration. We had for our transformed data, that it would be fit to 0.9591 minus 1.6698. So if we want to transform this back, we need to say YF, short for Y fit, is what I'm going to write. Actually, I'll clear that out. So we have YF will need to equal 0.9591. Then we do term-wise multiplication with x minus 1.6698. I put all of those in brackets because the last step here is that we want to square all of this. And I forgot, it needs to be term-wise exponentiation here, because MATLAB would have thought of the stuff inside of this bracket, or the set of brackets there, as being a matrix. So try that again. There we go. We have our Y fit. And so now we can go through and try plotting all of our data. So one sort of neat thing that we can do is we can plot multiple functions just by putting together sort of corresponding pairs of independent and dependent variables. So we have x, y, x, and then yf. And now plotted out, MATLAB will sort of by default use blue as the first pair, or for plotting the first pair, and then red for plotting the second pair, unless you specify with other options applied to the function. So we can see that after transforming our linear model fit back into the proper form, we get something that does fit the data rather closely.